Welcome to the course Excelling with Mathematical Modeling. In today's lecture, we will learn about the pre-predator models. So, already I have given you a little hint about this Lotka and Volterra pre-predator model. The first pre-predator model was initially proposed by Alfred Lotka. So, he used this equation to analyze the prey-predator interaction in his book on biomathematics. The same set of equation was published in 1926 by Vito Volterra, and who also became interested in mathematical biology. So, the history goes like this, that Volterra's son-in-law, his name is Umberto di Alcona. So, he was studying this fish. He was a marine biologist. So, he was studying the behavior of the fish, and during the World War in the year 1914 to 1918, he noticed that in the Adriatic Sea, the percentage of fish that were caught were not what he has expected. So, for example, the locals want a particular kind of fish that they generally accustomed to eat. But then during this period, what he find that some different fish was caught, which was a predatory fish, which means the fish which used to eat the fish that was a choice of the locals. So, that was the point of discussion between him and Volterra, and listening to that, Volterra created this model based on his observation, and independently he created this same set of equation that was created by Alfred Lotka. Though obviously he acknowledged is Alfred's work, and then this equation came to known as Lotka-Volterra pre-predator model. So, that is the history behind this model. So, if you consider the pre-predator model, as you can see in the video, that the predator here is the cheetah and the prey is the deer. So, it is a common thing that the predator will hunt down its prey for food only, and it is going to benefit in its biomass, the food which we all need. So, to model this, let us take this set of equations. So, this frog is your prey and the snake is your predator. So, this is my prey and this is my predator. This gives you the rate of growth or rate of change of growth of the prey, and this DDT gives you the rate of growth of the change of predator. So, if there is no prey, suppose this part is not there, then what happens is the prey grows freely at a rate say x. But when it comes in contact with the predator, obviously the predator eats the prey at a rate beta. And since it is eating the prey at a rate beta, its population decreases, that is why this negative sign is here. So, the growth, increase in population, that is why positive sign, the death because its interaction with the predator, that is why this negative sign. In the similar manner, if your predator does not get any food, then obviously it is going to die. So, that explains the first part, that suppose the predator is not getting any food, it is going to die at a rate gamma, and since it is dying, the population is decreasing, we have a negative sign. And since once it comes in contact with the prey, that is, if it gets food, obviously its population will increase, say at a rate delta, and hence the positive sign. So, this explains this particular cartoon. Now, if I replace this by the variable x, by the variable y, this is x, this is x, this is y, this is y, this is x, and this is y. What we get is called the Lotka-Volterra equation, and it will look like this. Now, next comes the analysis of this model. So, as you know that first you have to find the equilibrium solution. for which you put the values r x minus beta x y equal to 0 and minus gamma y plus delta x y equal to 0. If you solve these two equations, you will get the values to be 0, 0 and another value is gamma by delta and r by beta. Now, if you want to calculate the eigenvalue, obviously you have to calculate the matrix, which is fx, fy, gx and gy. So, if we take this to be our fxy and this to be our gxy, and then you calculate A minus lambda I equal to 0 to calculate the eigenvalues, and if you do that, you will get something like 0 minus lambda minus beta gamma by delta into delta r by beta 0 minus delta. And if we calculate our eigenvalues, it is going to be plus minus I square root of r into gamma. So, purely imaginary eigenvalues. If we now look into the numerical solution, so the initial values were x0 equal to 1, y0 equal to 1, your r equal to 0.4, beta equal to 0.4, gamma equal to 0.4 and delta equal to 0.6. So, if we put this value and solve this in Microsoft Excel, we will get the curve like this, where your blue is your prey and your red is the predator. Now, what is the interpretation of this graph? So, both of them starts with the initial value 1. Now, as you can see that the predator increases. The predator, as the predator increases, so if there is an interaction between the prey and the predator, so the predator is going to eat the prey and hence the population of the predator increases. So, you can see that the population of the predator increases, whereas the population of the prey goes down. And this is the maximum value where your predator has increases, but then the number of prey falls short and the predator is not getting enough food. So, then what happens? The population of the predator starts going down. This is going down, but at one point when it happens that the predators are also becoming less, and with the number of preys are there, so the predator is not able to catch the prey. So, then the prey again starts growing, and once they are in abundance, that means lot of prey, again the predator starts eating them and again it starts growing. So, there is a cycle between this dynamics of this particular prey predator model, and if you plot the phase portrait, your eigenvalues are going to be, if I substitute the values here, it is purely imaginary and you will be getting a center. So, basically you will be getting a curve like this. So, that is the dynamics of this Lotka-Volterra prey predator model. Let us now modify this model. So, the modification is that now you have, instead of Rx, I have taken the logistic growth, where your R is the intrinsic growth rate and K is your carrying capacity. So, again, if you want an explanation of this carrying capacity, consider this pond. So, this pond has lot of fish and they are all surviving. So, then you decided to add some extra number of fish. So, you put them, say you put 100 more fishes. Now, it is fine, 100 more fishes. Again, after a few days you want to push again 200 number of fishes. But then in the next day you find that some dead fish floats up. That means the environment cannot support that much amount of fish. So, that is exactly what this carrying capacity K does. So, it is that number which will tell you, okay, this is the number up to which the environment can support this particular species. So, that is this carrying capacity K. Beta is the rate at which your predator is killing the prey. Here this equation remains same. If the predator does not get any food, then it dies at a rate gamma, and if this gets food, it grows at a rate delta. If you want the analysis of this model, as usual, you take this to be fxy, this to be gxy, and then you find the equilibrium solution. If you put this equal to 0 and this equal to 0, your equilibrium solution will be 0 0, k 0 and gamma by delta into r k delta minus gamma divided by k beta delta. Now, since it is a population, it cannot be negative. So, for the existence of this particular equilibrium point, if this equilibrium point to exist, that this part has to be positive, which means that k delta minus gamma has to be greater than 0. So, this is the condition which you have to state such that this equilibrium point exists. Then you have to find the Jacobian matrix, which is A, and we have done this before. And you calculate this at the point x star y star. These two are simple, you will be able to do them. If I want these values, then after differentiating with respect to x, if I substitute these values on simplification, this becomes minus r gamma minus beta gamma by delta r times k delta minus r divided by k beta and 0. Now, if you want to find the eigenvalue, write the characteristic equation, which will look like this, plus r gamma divided by k delta times lambda plus r gamma 1 minus gamma by k delta. So, by Routh-Hurwitz criteria, if the equation is of the form lambda square plus a1 lambda plus lambda 2 equal to 0, then the system will be stable if both a1 is positive and a2 is positive. As you can see, these are already positive because the constants are positive. So, you have to take this r, k, beta, gamma and delta, they are all positive constants, because as they gives you the rate at which the prey is catching the predator, the carrying capacity, all are positive quantities. So, now if this system has to be stable, this has to be greater than 0, but this is obviously greater than 0 because you have k delta minus gamma divided by k gamma if you simplify this. So, this is always positive because of the existence of this equilibrium point. So, this system is always stable. Now, if you want to look into the numerical solution, so your x0, again I keep the same initial condition that your x0 is 1, your y0 is 1, your r is 1.3, your k is 1, beta is 0.5, delta is 0.7, gamma is 0.7, delta is 1.6. If you substitute these values, you will get a curve like this. So, if you calculate the eigenvalues, you will see that they give you imaginary one with conjugate pair with negative real part, and we know from before that if your eigenvalues are imaginary with positive real part, then you get a stable focus or a stable spiral. This is exactly what you got. So, this is your x axis and this is your y axis, and this is for the prey and the predator. So, the dynamics says that this will be a damping kind of circle, and after the damping it reaches this equilibrium point. So, this is a example of a modified prey predator model. Sometimes it is also called modified Lotka-Volterra model. Let us move to a next example of the prey predator model. So, this is a pelican and fish. So, this bird pelican, you can see that how it dives and it catches the fish, and they have this mechanism. The throat is so big that the fish is caught, and you can see in the video that it is struggling, and then it passes down through this particular hole in the mouth inside, and that is how the pelican eats the fish. It hunts and eats the fish. So, in this particular case, as you can see, the pelican is a bird. It flies, it dives down to the lake and catches the fish, but then the pelican does not have access to all the fishes. It has an access to a fraction of the fishes, and that is where we use the Halling type 2 functional response. To explain it more, so now your model is, this is the logistic growth which I have explained before. Now, this is the part of the prey, this is the Halling type 2 functional response, and y is your predator, in this case the pelican. And as I told you before, that x by x plus alpha can be written as 1 minus x by x plus alpha, sorry, alpha by x plus alpha. So, you can see that this represents actually a fraction of the fish that is accessible to the predator, in this case the pelican. So, this is the logistic growth, this is the rate at which the predator is eating the prey, beta is the rate, this is the functional response, how they interact, and sorry, this will be delta, and since the predator is eating the prey, it will add to its population, and hence plus delta times xy divided by x plus alpha, and if the pelican does not get any fish, it will die at a rate gamma. So, this is your prey predator model, where the predator does not have access to the whole of the prey, but only have access to the fraction of the prey. So, if you have to do the similar analysis, you take this to be f x y, this has to be g x y, and then you calculate the equilibrium solution. In this case, it will be 0 0 k 0, and this becomes k r delta into delta minus 2 gamma divided by beta delta minus gamma whole square and k gamma divided by delta minus gamma. So, this is the equilibrium point. And now, for the existence of this equilibrium point, because this is a population which cannot be negative, so delta has to be greater than gamma and delta has to be greater than 2 gamma. So, if I take this, the value is gamma, this value is 2 gamma. So, both of them need to be satisfied. So, this holds that if delta is greater than 2 gamma, then obviously it is greater than gamma. So, we will say that if this is the condition, then you have always this equilibrium point as a positive equilibrium point, and this equilibrium point will exist. So, the condition we will only pose here is delta has to be greater than 2 gamma. So, when you choose your numerical values, you have to be careful that this inequality holds, that delta has to be greater than 2 gamma. So, once you get your equilibrium point, then you calculate your fx, your fy, your gx and your gy. So, in this particular case at the point x star y star, your f(x) is k cube r minus 3 k r x star square, this is r, minus 2 gamma x star cube minus k square beta y star. This will be minus x star beta by k plus x star. This will be k times delta y star divided by k plus x star square, and this will be minus gamma plus delta x star divided by k plus x star. And you have to put either 0, 0 or k 0 or the other equilibrium point to see whether they are stable or whether they are unstable. So, if I choose the other equilibrium point, it is going to be k gamma by delta plus delta minus gamma, that is your y, and your x is equal to k or delta minus 2 gamma divided by beta delta minus gamma whole square. So, I want to check the equilibrium at this point x star and y star, and if you substitute here, your Jacobian matrix A is going to give you 2r gamma square minus beta gamma by delta. This is r times minus 2 gamma plus delta divided by beta and 0. Then you find the characteristic equation, and in this case it is going to be lambda square plus 2r gamma square by delta into delta minus gamma into lambda plus r gamma by delta minus 2 gamma equal to 0. Now, because of the existence of this equilibrium point, we must have delta is greater than 2 gamma, which will imply this to be positive and this also to be positive. So, by Routh-Hurwitz criteria, the equilibrium point x star y star, where x star is this and y star is this, is stable. Now, whether it is going to be, what kind of dynamics it will give, we can only verify it with the numerical solution. So, if you solve it numerically with these numerical values, you will get a graph like this. So, which says that in this particular case your prey grows and then comes to a constant value, which is the equilibrium solution, and the predator first goes down because it will not be able to catch the prey, and then when it starts catching the prey, it maintains a steady population. So, in a prey predator model, it is always expected that there will be a coexistence. The prey will also exist, the predator will also exist, one may dominate the other. But if one of the species goes to 0, then this is something against the nature, because then that particular species is endangered, means they just go extinct. So, that generally does not happen in a real life situation. So, this kind of behavior or this kind of dynamics is expected. And if you want to see the phase portrait, so you can see that this is the eigenvalue here with this particular numerical values. So, both are real and negative, and we know that we get a stable node. So, only thing is I do not have the arrow here. So, if this is the equilibrium point, so it is a stable node. So, I have to put the arrow like this because it is stable. So, with this we come to the end of this lecture, which discussed 3 kinds of prey predator model, and depending on the situation you just go on modify these models. In our next lecture, we will be looking into some competition models. Till then, Bye bye.